All right, so some more examples of the second derivative test. And I think I alluded to this a little bit in the last video that analyzing a graph, especially like a first derivative graph, is so common on the AP exam because a first derivative is sort of like the result of the function's derivative. So you can kind of know some things about the original function seeing the derivative, but then you can also take its derivative to start looking at the second derivative. So, like knowing, I guess, what you're looking at now becomes so crucial. So knowing that, yes, this is the first derivative. Okay. And so when you have a first derivative and you're talking about decreasing, remember anything that's below the x-axis tells you that the first derivative, those y values, are less than 0, that means it's going to be decreasing. So I know it's decreasing. And again, I don't know. I should look ahead. Yeah, so assuming this goes on forever, there's not arrows. You usually have a definite endpoint, but assuming it goes on forever, if that was an arrow, and that's an arrow, then we would say it's decreasing from negative infinity up to, now remember, you can include this point since it doesn't ever change signs. Like that can just be one continuous interval, or you could split into two. And that goes 1, 2, 3, 4, 5, 6, 7, 8. So negative infinity to 8. How do I know it's decreasing? Because f prime of x, because that's what I see, is less than 0. And don't tell me it's lower than the y-axis, or it's below the x-axis. No, don't tell me that. That's what you're looking for, but then you have to interpret it in terms of that first derivative test. The first derivative is less than 0. The first derivative is negative. So you could say like a good complete sentence would be f of x is decreasing on this interval because the first derivative is negative. Perfect. Now, when is it concave up? So now concave up is when, like, we're looking for when is the second derivative positive. But you aren't looking at the function, so you can't just look at the curvature. You're not looking at the second derivative graph, so you can't just look, is it above the x-axis? You've got to interpret, I'm looking at the first derivative. So how do I measure the second derivative, because that's concavity, when I'm looking at the first derivative? Well, it's the slope of f prime. So I want the slope of f prime to be positive. So concave up, so I could say f of x, because we're analyzing f of x, even though we can't even see it. F of x is concave up when, let's see, concave up. So that we want the slope of this line to be positive. So that's happening here, right? Positive, 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 up to that point. And then maybe starting here, positive, right? Because if the slope of that line is positive, right, the slope of the tangent line of the first derivative is positive, it means the second derivative is positive. So I could say it's concave up when, again, I say like negative infinity. And now this time that's up to 1. Union. And then let's see, what is that? 1, 2, 3, 4, 5, maybe 5.5, like approximately 5.5 to infinity. So it's concave up for these intervals. And how do I know? Because the second derivative is positive there. But I can't just say the second derivative is positive. I have to relate it to what I physically can see. So how do I know that second derivative is positive? Because slope of f prime of x, because remember, I visually can see, I know that sounds redundant, but I can see the derivative because the slope of f prime of x is positive. Okay. Identify the x-coordinate of each point of inflection. Are any of them saddle points? So we want to know, when do we change, like this, when does the second derivative change signs? And so if the second derivative is measured by the slope of the first derivative, then we can see that we change signs here and here, right? Because here's where the slope was positive. Here's where the slope is negative. Here's where the slope is positive. So I know that 1 and 5.5, those transition points where we're changing from concave up to concave down or vice versa, are my points of inflection. So to identify them, I'd say, okay, yes, x equals 0 and 5.5. are points of inflection. And I can't just say, oh, the second derivative changes signs, because that's just the blanket general definition. So how do we interpret the second derivative changing signs when you're looking at a first derivative graph? So I could say points of inflection because slope of f prime of x, because remember I can see f prime, and so I can measure the slope, because slope of f prime of x changes signs. And again, it doesn't really matter if it's positive to negative or negative to positive. What matters is that it changed signs. So perfect. So are any of these saddle points? Now, how do you tell if you're a saddle point? A saddle point means that its first derivative is also 0. And how do you know when the first derivative is 0? It sits right along here. So the two zeros are 1 and what is that? Whatever that is, 6, 7, 8. And of the two, this is both, like, remember that was a point of inflection. It's a point of inflection whose first derivative is 0. So then, yes, it is. X equals 0 is a saddle point. So not only is it a point of inflection, it's very specialized. It's a saddle point. X equals 0 is saddle point because f prime of 0 is also equal to 0. So it's a point of inflection whose first derivative is 0. Okay. Again, let's do a same kind of analysis with this graph. It is the first derivative. So if that's the first derivative and we want to measure concave up, you want to look where the slope of this derivative is positive. So concave up, where do we have positive slopes? Here, here, and here. So I would say from 0 to 1, union 1, 2, 3, 4 to 5, union 6, 7, 8, 6 to 8. How do I know? And I can't just say, oh, the f double prime is positive, because I don't see the f double prime graph. So I need to interpret it based on what I see, which is the first derivatives graph. So this concave up because slope of f prime of x, because that's what I see, is positive. So as soon as you talk about slope of f prime, that's like the second derivative. Your like interpretation, hey, this is the second derivative. So this is how I'm measuring the second derivative. It's the slope of the first derivative, and that's what I see. Concave down, let's let that slope be negative. So now we're talking, right now we're talking from 1 down to 4, and then looks like from 5 to 6, and then also from 8 to 10. So we could say from 1 to 4, and then we said from 5 to 6, and then we said from 8 to 10. And how do we know? Because slope of f prime of x, which I can see, is negative. And again, the slope of f prime is how we're measuring second derivative. And we can't just say this. We have to say, well, we have to interpret, how am I seeing f double prime? Oh, I'm seeing the slope of f prime. Awesome. Okay. And then very common, points of inflection, are they saddle points? So we're looking for slope change signs. And that's right here at 1, at 4, at 5, at 6, and at 8. So 1, 4, 5, 6, 8. 1, 4, 5, 6, 8. And you'll get used to knowing that those are kind of like the peaks and the troughs, right? That's where they change signs. So how do you know? Because slope of f prime of x changes signs. And notice that technically at those points, they're not even zeros. Those are cusps. So they're actually undefined, right? But it's okay. It's either being 0 or undefined, but then changing signs. And you don't have to say, well, this one goes from positive to negative. Oh, and this one goes from negative to positive. Because it doesn't matter. As long as you've changed a sign, then you're a point of inflection. Now, of those, are they any saddle points? And remember, saddle points have to have a first derivative equal to 0 as well. So, again, thinking about visually, okay, well, if you sit on the x-axis, your first derivative is also 0. So right there is my saddle point. but I can't just say, oh, because it's on the x-axis. So interpret, it's a saddle point because it's a point of inflection whose first derivative is also 0. So I could say it, oops, my bad, pen for that color. So I could say like x equals, what was it again? Oh yeah, 5 is a saddle point because f prime of 5 is also 0, right? Okay. Then I think there's one more where what if we have the exact same image, but now that image represents the second derivative? So if this represents the second derivative, then now this x-axis separates things that are above. If it's positive, those y values, then we know we're going to be concave up. And if it's below the x-axis, those values are negative, then it's going to be concave down. So I can easily see the sign. Is it positive? Is it negative? So when is it concave up? As long as I'm above the x-axis. So as long as I'm up here. Oops. I don't know why I selected that color. That's great for writing, not so much for highlighting. So I'm trying to highlight this. Maybe there's just a delay. There it is. So concave up at those points. So oh yeah, pen, and maybe we'll go to this nice kind of bluish green. So it's from 0. Actually, I can include 0 here because that's still positive. Try to include 0. Man, I'm just malfunctioning left and right here. Oh. Okay, one more time. Third time, fourth time, fifth time's a charm. There we go. So from 0 up to 1, 2, 3, but now it's open-ended there because that's a value of 0. Here, that's a positive 2. So it definitely is concave up. And then here from, what is that? 2, 3, 4, 5, 6, 7 to 9. 7 to 9. And how do I know? Because since I'm looking at the second derivative, I can actually say f double prime of x is positive for those intervals. Because that's what I see. Okay, when is it concave down? You could make these two separate, or realizing that since you're not changing signs, you're still concave down. So I could say from 3 to 7, and then from 9 to 10. 3 to 7 union 9, and you can actually include 10 because its value is negative 2 as a y value. And how do you know? F double prime of x is less than 0 for those intervals. So there's not as much we can analyze when you see a second derivative, but you just want to make sure you realize what are you looking at? Looking for things below the x-axis. Any values where there's a point of inflection. So again, points of inflection happen when f double prime of x changes signs. So that is always going to be the same. You just have to figure out, given what are you looking at, how do you interpret that? Are you looking at the function or the first derivative or the second derivative? If I'm looking at the second derivative, where do you change signs at? Well, you change signs where you go from positive to negative. So there are 3, right? So from here, here, here. Now this one is suspicious because technically it's 0, but it doesn't change signs. So we throw it with that one does not count. So it's just, right? So it's just 3. It's just 7 and 9. And I mean, in hindsight, look at those are your transition points, right? 3, 7, and 9, right? Those are where you're changing from concave up to concave down. That's the definition. So POI, x equals 3, 7, and 9. How do I know? Because f double prime of x changes signs. And I can legitimately leave that as my reason because I'm seeing the second derivative. Now, are any of these saddle points? Well, the thing is, how do you know you're a saddle point? Your first derivative must be your first derivative must equal 0. So, looking at a second derivative graph, how do you tell your first derivative is 0? Okay, long pause, let you think, but you can't. That's the thing. You have no idea. You lose that bit of definition of that function every time you take a derivative, and you can't go back. So I don't know what the first derivative is here. I don't know what the first derivative is here. and I don't know what the first derivative is there. So I don't know. There might be, I don't know. So that's kind of like a trick question. Are any of these saddle points? We don't know, cannot be determined, because we cannot decide what that first derivative is. Now, some of you might also be wondering, well, wait a minute, could this be a saddle point? Because notice it doesn't change signs, but be careful what doesn't change signs. The second derivative doesn't change signs. So it's not like it's the first derivative not changing signs, it's the second derivative. So if your second derivative is not changing signs, you never were a point of inflection to start with. And if you're not a point of inflection, then there's no way you could be a specialized point of inflection, which is a saddle point. So, you know, and I totally understand where you're coming from, because this is a feature of a saddle point when you see a first derivative graph. But don't be distracted, because that is not a feature on a second derivative graph. And, you know, again, thinking about how will the AP exam assess you, they're going to give you, you know, they could give you that same image and say, hey, pretend it's a function. What do you see? Pretend it's a first derivative. What do you see? Pretend it's a second derivative. What do you see? So it reminds me of like the brown bear, what do you see? You know, that book. So, okay. Big topic. And so I know, again, I'm spending a little bit more time on these videos because I want to give so many explanations, and I want you to hear it so many times, because you need to know that and be really, really, I guess, proficient at solving and analyzing these questions. And I know when we get to class on Wednesday, you know, you'll have lots of practice to like say, hey, here's a first derivative graph. What's happening to the function? Because that's going to be such a crucial skill to know. And it'll be a big part of our quiz, which I think will be on Friday. Okay, so very good. And then let me go ahead and pause the video and, you know, go ahead and start the homework and check in with me if you have any questions.